let's talk about polynomial functions. The definition of a polynomial. And the IXLs that that are scheduled for tomorrow during e-learning, you should be able to do with our discussions from today. So here's a polynomial. A, B, C, D, and E are all real numbers. The leading coefficient, which is A, cannot be 0. N can be any non-negative integer. So, and if you notice, N's are the exponents. N is the exponent here. None of the exponents can be non-negative. They all non-negative integers. So all the exponents in the polynomials have got to be non-negative. The polynomial's function is degree n, where n is the greatest exponent that you see, the largest, and a is the leading coefficient. And if you look at this term right here, this is ax to the n, bx to the n minus 1. That's if n started out 5, n minus 1 would be 4, and then we would have 3, 2, 1, 0. So that's why the n minus 1, n minus 2. Quadratic functions, those are linear. Those are polynomials. Linear functions are polynomials. Constant functions are polynomials as well. So here's a couple examples of polynomial functions. I have f of x is equal to this 5x to the 6, 7x cubed minus 2x squared. This is a polynomial. The degree of this polynomial, let's put that somewhere right here. The degree is 6. The degree of that polynomial is 6. Because of that 6 right there. The leading coefficient, if you will, A is equal to 5. And notice, if you recall about quadratic functions, the A is a very important leading coefficient. If A is positive, it opens up. If A is negative, it opens down. That has a lot of connection to what we're going to be talking about momentarily with the leading coefficient. Okay, so that is a polynomial. And n or any has always got to be a non-negative integer. And if this is an integer, that's an integer. All the exponents are integers. That's what that means. And for a polynomial, all the exponents have to be integers. This guy right here, is this a polynomial? This is a polynomial as well. Here, the degree of this polynomial is 4, and A, the leading coefficient, is negative 2. Okay? Here are some examples of non-polynomial algebraic functions. Just because it's algebraic doesn't mean that it's a polynomial. This is not a polynomial because if you notice, this guy right here, this could be written x to the 1/2 power, because I could take this radical and make it a degree, x to the 1/2 plus 4x plus 8. So what makes it a non-polynomial is this 1/2 right there. That's a non-polynomial because the exponent is 1/2. Exponents have to be non-negative integers. This guy right here is also a non-polynomial. This is a non-polynomial because why? Because this exponent of negative 3 is negative. It's not non-negative. It's negative. So this is not polynomial, not poly. No poly. Since the exponent is negative 3. Non-poly, the exponent is 1/2. Down the road, some of you, not all of you, some of you will jump into Calculus 2, which is BC. Well, you'll do, and we'll talk more about that next year. We do a combination of Calc 1 and Calc 2. I am writing a really, really nice curriculum similar to this for Calc 1 and Calc 2. I've been wanting to do that for years. But some of you will do the Calc 1 and Calc 2 at the same time. One of the most important topics in Calculus 2 are Taylor polynomials. And why we study them in Calculus 2 is because of this property, this very important properties of polynomial functions. And here are these two main properties of polynomials. The domain is all real numbers. The domain is all real. So if somebody asks you, you know it's a polynomial, they ask you the domain, boop, the domain is all real numbers. That is, the graph is continuous for all x values. And we talked about what discontinuity for us at this level means that you have to pick up your pencil when you sketch the graph. You can always sketch every polynomial in one swipe. You never have to lift up your pencil. So that is an important property of polynomials. The other important property of polynomials, the graph of polynomial function is smooth. That is, there are no sharp corners in the graph. It's smooth. Don't write this one down, but that's not a polynomial because that's not smooth. Here's smooth. Smooth. Those are smooth. Polynomials are smooth. A very important, I'm going to erase these. A very important property of polynomials is that it's smooth. And I will ask you next year, hey, what are those two important properties of polynomials? And you will say, oh, I remember. They're continuous and smooth everywhere. So polynomials are smooth and continuous everywhere. That's why we can talk about these Taylor polynomials down the road. Okay, so now we're just going to talk about what the graph of a polynomial looks like. So when we talk about the range, if n is an odd number, like if the degree is odd, if the degree of the polynomials is odd, the range is all real numbers. If n is even, say x squared, oh, well, quadratic function, the range is not all reals. A quadratic function is either y is greater than or equal to the y coordinate of the vertex, or y is less than. But that doesn't mean if n is even, there is a restricted range on all even degreed polynomials. All it is if n is even, there's going to be a little work to do to determine the range of the function. But there's going to be two cases of the degree. Two cases for the degree. The degree is either going to be odd or even. And it looks like the first case. So the end behavior, this is a little bit. The end behavior of polynomial describes what the graph of the polynomial will look like toward the end of the graph. And what I'm going to do I'm going to go to a blank screen and try to explain end behavior. A little bit, because it's really an easy concept. When we talk about the end behavior, we're going to talk about, we know that this is the y-axis, and we know that this part of the y-axis right here is positive. This part of the y-axis is negative. I don't know if you had room or not. You might just think about this. I don't know if you had room in your book or not to add this somewhere, but you don't have to worry about it. There's a page right to the end, but if you just think about this for a minute. Okay, so we're going to talk about end behavior. If I had this graph right here, it's polynomial or continuous everywhere. So the graph, I'm going to say that that graph goes y infinitely high forever. I'm going to say this graph comes down here and does this. And the arrows denote that this thing is going to go up forever and ever. This particular graph, we say starts positive. Why does it start positive? Because it's in the positive portion of the y's. Y's are either negative or y's are positive. This graph here starts positive because it's going to start way over here. It's going to start way, way, way over here. We don't even know where it starts. But I do know that polynomials are continuous everywhere. So this thing starts positive, and then it ends negative. So on the end of this graph, this is going to be positive and negative. That positive and negative refers to the y values. Positive y values or negative y values. That's what it means when a graph begins or ends positive. So let's go back to that. Might help a little bit because people struggle. Okay, here we go. If I have an n, if n is odd, if the degree is odd, and a is positive, if the leading coefficient is positive, and the degree is odd, then the graph of the polynomial will start negative and end positive. Here is an example, and I'm going to do a little example for each one of these guys right here. Okay, and I'm going to do the graphs in green. The graph starts negative, and we don't know what happens. We don't know what the heck happens, but it's going to end positive. There could be 1,000 different things that happen in here. We don't know. You might would dot it. All we know is if n is odd, if the degree is odd, and the leading coefficient is positive, the daggone thing starts, get out of here, starts, starts negative down here. Woo, don't know what it does between this beginning and end, but it starts negative and ends positive. Okay? If n is odd and the leading coefficient is negative, if n is odd, if the degree is odd, the leading coefficient is negative, then the graph of the polynomial will start positive and end negative. So what's going to happen here, and I think you have room enough to put this in here. So the graph is going to start positive. It's going to start up here at the positive y's, and we don't know what's going to happen. It could cross the x-axis 1,000 times, but we know it's going to start positive and end negative. And we don't know what's going on between the two. Okay? So we don't know. And one of the things we're going to investigate later on is what, if we're given some polynomials, what's going to happen at the end, in the middle. So that's the two graphs of if you have a odd degree. If it's odd degree, leading coefficient is positive, starts negative and ends positive. Leading coefficient is negative, starts negative, or start positive and ends negative. Okay, now I talk about if n is even, if the degree is even. If the degree here is even. If the degree is even and the leading coefficient is positive, then the graph of the polynomial will start positive and end positive. Here we go. What's that look like? That's going to look like this. Let's see here. Oh, it starts positive. Let's go blue. Starts positive. We don't know what's going to happen in the middle. Have no idea. But it's going to, if n is even and the leading coefficient is positive, the graph starts positive and ends positive. there has to be a restricted range. The range can't be all real numbers. Here, on these two examples, the range is all reals. And we know the range all reals here, range all reals here. This has to have a restricted range. We know on both of these the domain is all reals because that's a property of polynomials. Okay, so now if I have this guy right here, n is even and the leading coefficient is negative, what's going to happen? The graph is going to start negative and end negative. So it's going to do this. We don't know what's going to happen. Could just do that. Start negative and end negative. We know it's going to be connected because it's a polynomial. Okay? This is very, 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 very important. All right, questions about end behavior. So jumping ahead, polynomial functions in factored form. Many times a polynomial function will be presented in factor form. This form makes it really easy to find the x-intercepts, the end behavior, and to graph the function. Similar to other functions that have been discussed, the zeros of a polynomial are the x-intercepts of the graph of the polynomial. When it's in factored form, we should immediately see the x-intercepts. And the x-intercepts of this polynomial, that's when the output is 0. You can look right in that graph. Oh my goodness gracious. And look at this. Bam. When is that guy 0? If I wanted to find out where that guy was 0, hello. I immediately see it's going to be 0 at x equals 5, x equals 1, and x equals -3. Those are going to be the x-intercepts of that graph. So the x-intercepts of that graph are going to be 5, 0, 1, 0, and -3, 0. Immediately I see that these are the x-intercepts. All right. What's the y-intercept of that guy right there? What are the y-intercepts? Well, you find the y-intercepts by letting x equal 0, true or false. If you let x equal 0, find the y-intercept. Look at what you have. You want to find f of 0. What's f of 0? F of 0 is going to be -5 times -1 times +3. -5 times -1 is 5 times 3 is 15. So right away, if I have this in factored form, I can see the x-intercepts and the y-intercepts pretty daggone quick. 0, 15 is the y-intercept. Okay, we will talk more about power functions down the road, but if I want to graph this guy, and here's the essence of if I were going to multiply this out. So right now, what we're going to do is we're not going to bypass this part right here. And what we're going to do, if I want to, what's going on here? Why can't I do this? Here's my function right here. This is a difficult topic for a lot of good math students, because if I wanted to ask you to multiply that out, you would be able to multiply that out. How would you multiply it out? You would multiply these two binomials first. You would get this trinomial and use the distributive property and multiply it by this binomial. We're not going to multiply it out, and we don't have to multiply it out. If I did multiply it out, we're going to act like we multiplied it out, because I want to see the end behavior. I want to see the degree, and I want to see the leading coefficient. If I were to multiply it out, could you tell me what the very first term would be? The first term, and it's really easy to find, the first term is going to be x times x times x is x cubed. We don't care about the middle. We're just going to go plus dot, dot, dot. If I were going to multiply that out, what would be the last term? The last term would be 15. Negative 5 times negative 1 times 3. So that's that polynomial multiplied. Well, not really. It's that polynomial, not really multiplied it out. But we're looking at the first term and the last term because those are the only terms we need to look at to graph. And now I'm going to ask myself a question. N is odd. The degree is odd. The leading coefficient is 1. So now I have 3 is odd. 3 is odd. A is equal to 1. 3 is odd. A is equal to 1. And if I go back to my original notes, what does that tell me? Let's see here. Odd, positive. Odd, A is positive, N is odd. Starts negative, it ends positive. Starts negative, it ends positive. Oh. Starts negative and ends positive. The other thing I know about this factored form, I know what the x-intercepts are. Whoop, right there. There's your negative 3, 0. There's your 1, 0. And there's your 5, 0. So I have this. I have 5, 0. I have 1, 0. And I have negative 3, 0. And I found those up here. Bam. What else? What other point did I find? I found this point right here. What point is this? 0, 15. What more is there on that particular graph? And look, the graph is, it's smooth. It's smooth. Smooth and continuous. The other thing that you could do is now, since we have a graphing calculator, I can find the max and minimum, the relative maximum, relative minimum points. And I actually did this in this example. So I've actually found this minimum point right here. This minimum point is this guy right here. This is that 3.309, negative 24. This is that point right here. Let me go up a little bit. This is that maximum point, negative 1.309 and 24 point. Okay? And now we can talk about where this particular polynomial increases and decreases. We know a graph increases if when you're moving from the left to the right, the graph goes up. And this thing increases from negative infinity way down here, but it increases, I'll do increasing in green, it increases all the way to the x-coordinate of that maximum point right there. And then it starts increasing from this x-coordinate, and that's where the daggone thing increases. That's what we're talking about here. Where does that graph decrease? That graph decreases, let's do decrease in red, from this point to that point. Therefore, the x-intercepts are negative 5, 0, negative 1, 0, 1, 0, 3, 0. Find the first, do not multiply it out. X times x times x times x is x to the fourth. And then if I 5 times 1 times negative 1 times negative 3 is 15. And I want the end behavior. N is even. 4 is even. 4 equals n is even. A, the leading coefficient, is 1. So this bad boy starts positive and ends positive. It has a y-intercept of 0, 15. Look how quick I can graph this polynomial without my graphing calculator. It's going to happen with your graphing calculator. You have to change your window in here. But look at this. Plot the x-intercepts. Know the end behavior. Plot the y-intercepts. Bam, you got the graph. And there it is. You got the x-intercepts, you have the end behavior, you have the y-intercepts,